Welcome back to the class on power semiconductor drives. In the last class, we have seen the three-phase fully controlled converter with a DC motor or a constant load current. In this class, we are going to discuss about the three-phase off-controlled converter with a DC motor. Off-controlled converter is nothing but a semi-converter. This is the circuit diagram of a three-phase off-controlled converter with a DC motor. This is the load. The field winding is excited with a separate DC source. When the load current is passing from the top to the bottom, that you have to take it as a positive direction of the current. These are the positive group of SCRs, T1, T2, T3. These are the negative group of diodes, D1, D2, D3. SCRs are nothing but control device, where the diodes are nothing but uncontrolled device. No need to apply any triggering pulse to the diodes. These diodes are goes to the on state whenever the input voltage is more negative. Nothing but the D1 is goes to the on state whenever the A phase is more negative. D2 is goes to the on state whenever the B phase is more negative. D3 is goes to the on state whenever the C phase is more negative. Again, to analyze the circuit, we are going to take the 6 line voltages. Already we know how to draw the 6 line voltages. This is the zero line. This is x-axis. On x-axis we have taken the omega t. This line is representing maximum line voltage. This is representing the negative value of the maximum line voltage. Every 60 degrees we are going to draw a one vertical line. So finally we have taken one more line at a 360 degrees, because we are going to draw the input voltage only within the one cycle. This is the VAB voltage. The starting point of the VAB voltage is 0. Next, VAC voltage, the starting point is 60 degrees. Next, VBC voltage, the starting point is 120 degrees. Next, VBA voltage, the starting point is 180 degrees. VCA voltage, the starting point is 240 degrees. Next, VCB voltage, the starting point is 300. So to analyze the circuit, we have taken the firing angle alpha equal to 30 degrees. So whenever you are taking the alpha equal to 30 degrees, the firing angle which is after the T1, that you have measured from the 60 degrees. So at 90 degrees, nothing but at this point, the T1 is on 90 degrees. Once the T1 is on, it has to conduct a 120 degrees up to here. Next, T2 is conducting, because in the sequence the T2 is there. Next to 120 degrees, T3 has to conduct. So the positive group of SCRs are completed. Now come to the diode. For the diode, no need to apply any triggering voltage to the diode. Now you have to identify the region in which the phase is more negative. Suppose 0 to 120 degrees, B phase is more negative. So in this region, D2 is on. 120 to 240, C phase is more negative. Nothing but a D3 is on. So from this point to D3 is on. Again, 240 to 360 degrees, A phase is more negative, because A is second subscript. So D1 is on. This is the conduction of the, here small mistake, these are the diodes. This is the conduction of the diodes. Conduction region of the diodes. The conduction region of the diodes is not depending upon the firing angle. It is only depending upon the when the particular input voltage is more negative. Next, the instant of the SCR is on is highly depending upon the how much firing angle we are taking. In this case, we have taken the firing angle alpha equal to 30 degrees. That you have to keep in mind. Now, these are the conduction of the two devices. So from this point to this point, T3 D2, here T1 D2, here T2 D3, T2 D1. From this point to this point, T3 D1. See, this is the table in which we are going to see the positive group of S when it is conducting. See here, the T1 is conducting from the 90 to 210, because we have taken the firing angle is 30 degrees. T2 is conducting from 210 to 330. T3 is conducting from 330 to 360, again from 0 to 90 degrees. But the conduction of the D2, D3, D1 is fixed. D2 is conducting from 0 to 120. D3 is conducting from 120 to 240. D1 is conducting from 240 to 360 degrees. It is not going to change. It is independent of the firing angle. To develop the output voltage, here we have taken the first this region we have taken T1, D2 is conducting. So what is the waveform is there from this point to this point, the same waveform is repeating. So we are trying to find out what is the wave shape in this region. T1, D2 is conducting. The T1, D2 is conducting T1, D2. T1, D2. Upper terminal is connected to A, whereas lower terminal is connected to B. So the output voltage becomes a VAB. Now you go up and see how the VAB changing from maximum value to the some value. So that we represented here. Again at this point, T1, D3 is conducting. So T1, D3, nothing but a VAC. At this point, again, the output voltage VAC. So you take up this waveform. So you are getting this waveform in this manner. So once again, I repeating the same. From this point to this point, the output voltage is VAB because T1, D3 is conducting. Again, from this point to this point, VAC, T1, D3 is conducting, the output voltage is V. The same waveform will be repeating. But here, T2, D3 is conducting. The T2, D3 is conducting T2, D3, nothing but a VBC. Go up and see. This is the waveform, VBC. We take up the same. Next, VBA. In that manner, you complete the output voltage wave. If you observe the output voltage waveform, within the 120 degrees, what is the waveform is there? The same waveform will be repeated. Here, you have taken the load current is constant load current. So, load current is a constant. ICB current is nothing but from this point to this point. This is up to here, ICB current. This current is nothing but IAB. Again, from this point to this point, IAC. This is IEBC. This current is nothing but from this point to this point, IBA, again ICA. Okay. Now we are going to find out the average output voltage. To find the average output voltage, we should know what is the repeated waveform. This is the waveform which is repeating. This is the waveform which is repeating. So we have to find out the area under this curve. First, you have to identify this point, time interval. Again, this time interval. Again, this time interval. So here, this is nothing but a VCB. This time interval we can write it as a, see, this time interval is nothing but a on state of T1. So this we can write it as a pi by 3 plus alpha. This time interval is nothing but a half of a D2. It is a fixed, it is not depending upon the firing angle. So how much it is? It is 120 degrees, nothing but a 2 pi by 3. Now again from this point to this point, this is a, again it is depending upon the half of a T1. Nothing but this time interval we can write it as a pi by 3 plus alpha plus 2 pi by 3, nothing but a, we are getting a pi plus alpha. So this time is nothing but a pi plus alpha. So now we have to do the integration. When you're going to do the integration here, see here I am writing, because why you are going to do the integration is to find the area under the curve. Integral pi by 3 plus alpha to 2 pi by 3. This is VAB voltage into d omega t plus integral 2 pi by 3, nothing but this interval to this interval, pi plus alpha. This is VAC. VAC is nothing but a VML into sine omega t minus pi by 3. This is the expression for the VAC into d omega t whole divided by 120 degrees, nothing but 2 pi by 3. So in the numerator you can find the 3, the denominator you can find the 2 pi. This is equal to V0. Now we have to complete this integration. If we complete this integration, we are finally you are getting the one expression that is equal to 3 VML by 2 pi into 1 plus cos alpha. This is the expression for the average output voltage. In this manner, we can derive the average output voltage. The speed torque characteristics of a three-phase off control converter with a DC motor. The average output voltage is equal to just now I have seen 3 by 2 pi, limits from pi by 3 plus alpha to 2 pi by 3 VML sin omega t T omega t plus 2 pi by 3 pi plus alpha VML sin omega t minus pi by 3 into T omega t. If we complete this integration, VML take outside and substitute the limits. So finally, you are getting the expression. The average output voltage is equal to mathematical armature voltage is equal to V equal to 3 VML by 2 pi into 1 plus cos alpha. This you have to take it as a equation 1. Average output voltage is nothing but a armature voltage because that voltage we are applied to the armature of a DC motor. Now, already we know the general expression for the speed torque characteristics of a DC motor. This is the speed torque characteristics of a DC motor. Speed equal to V by K minus P into RA by K. In place of PA, you substitute the equation 1. Then you are getting the speed equal to 3 VML 2 pi K into 1 plus cos alpha plus minus P RA by K. This is the final expression for the speed torque characteristics of a shunt motor with a semi-converter. Now we are going to draw the characteristics of a DC shunt motor with a three-phase off control converter. On the x-axis you take the torque, and the y-axis you take the speed. Take at alpha equal to 0, nothing but how much voltage it is giving me. So you substitute alpha equal to 0, we are getting the 3 VML by pi. This value becomes a 2, 2 gets cancelled. Finally, we are getting 3 VML by pi. This is the voltage. This voltage we are adjusting such a way that equal to the rated voltage of a motor. So at this point, this point is represent no load. So as the load is increases, the speed of the motor will be decreases. When alpha equal to 30 degrees, then the initial no load speed of a motor will be decreases. From that point, if you increase the torque, the speed of the motor will be decreased. In the same manner, it is happening for alpha from 90, 120 also, 180 also. 180 you are getting a 0 voltage. Over the range of alpha from 0 to 180 degrees, the circuit is giving only the positive voltage. It does not give the negative voltage. Nothing but by means of a three-phase off control converter, we can get only the first quadrant operation. It does not give the second quadrant operation. But it is very simple circuit because it requires only the 3 SCS and 3 diodes. Some loads requires only one quadrant operation. Then we can go for this continuous load current of the. Just we are going to summarize what are the points we have discussed. We have seen the operation of the three-phase off control converter by taking alpha equal to 30 degrees. Next, we have derived the expression for the average output voltage. We found the what is the relation between the speed and torque in case of a three-phase off control converter, which is feeding a DC shunt motor. So thank you very much. If you have any doubt, you can ask me directly, or you can ask in the comment box of my YouTube channel, so that I am available to answer all your questions.